All right, guys, we're going to go over example 13.4 in your online textbooks. This is from section going over energy in SHM. This is on page 430 of that textbook, if you want to follow along. That's titled Velocity, Acceleration, Energy in SHM. So looking over the problem, it says in the oscillation described in example 13.2, that again would be something like this. Something oscillating back and forth, horizontal spring. We have a spring constant of 200 newtons per meter, a mass attached to it of 0.5 kilograms, and the oscillating mass is released from rest at x equals 0.02 meters. Now, since it's released from rest at that position, that automatically the amplitude we'll see. First, let's focus on part A. Find the maximum and minimum velocities attained by the oscillating body. So the max and min velocities would occur at the positions through defining energy from the formula earlier in our notes. So let's flip over to my solution. They're easier to follow. And pay no attention up here, by the way. I know it says example 14.4. These were written for our new textbook, but this is the same problem as 13.4 in the online one. So you'll notice I listed my givens, and I did put, as I described earlier, that since it was released at the x position of 0.02, that was actually our amplitude. All right, so I'm going to solve first this equation for v sub x, or just v. I'm going to isolate it first, and then we'll use that to solve part A. So if I isolate it algebraically, I could get it to look like this expression down here. Now, I know in the notes we noted if we are looking for max velocity, that we could immediately plug in 0 for that expression, and that goes away. You could do that because that is what we're looking for, but I just generically solve it here to be able to use for any x position, any horizontal position. So if it was 0, which it's going to be in part A because we want its max and min, it turns out that this portion goes away because it's 0, and the square root of a squared is just a, and it can be written like we showed in the notes. But either way, it's pretty simple. So as described in the notes, the maximum velocity of an object in SHM through energy methods could be found when potential energy is at its least, or 0. That's why we plugged in x equals 0 there. That means kinetic energy is at its greatest. And remember, when we solve for a quantity like v, where it has a square and we take its square root, the answer could be plus or minus algebraically. And that actually gives us both the max and min. The max going one direction through equilibrium is positive 0.4 meters per second, plugging in the numbers. And going the other direction, it's negative 0.4 meters per second. So that's all we really got to do to solve part A. Let's flip on over and look at what B asks. It says compute the maximum acceleration. So let's go back to our work over here. The maximum acceleration would occur when the force is the greatest. Now, the reason why is because although we're not really using it formally, the idea of Newton's second law, F equals ma. So the maximum acceleration would occur where the forces are the greatest. Well, where are the forces the greatest? When we have the maximum potential energy. That's when it's max stretch or max compression. So there or there is when that occurs, and that would be at its maximum amplitudes. The amplitude was given, if you recall, as 0.02. So we find a formula for acceleration from the notes described, and that general formula is acceleration, horizontal acceleration, a sub x equals negative k over m times x, the x position being those most stretched or most compressed. So that would be 0.02 or negative 0.02, depending on whatever you decided direction is. So we plug in those values, and we could see, solve for 0.02 and also negative 0.02, we would get 8 meters per second squared or negative 8 meters per second squared. And that just depends why there's two possible answers there, is because one way, when we're max stretched where my cursor is here, the acceleration is going in this direction. And when I put my cursor here as max compression, the acceleration, the spring is forcing it to the right. So at both positions, we have the same magnitude. That's what really matters. The positive one's the max, the negative one's the min. All right, going on to part C then. Seeing what it asks. Same situation. Determine the velocity acceleration when the body has moved halfway to the center from its original position. So its original position was 0.02. So obviously we just cut that in half in this step here, and that's 0.01. We use the same formulas we used in part A and part B, and everywhere I plugged in 0.02 in parts A and part B, I'm just going to simply plug in 0.01. And doing that, we can see we'll get for the velocity negative 0.35 meters per second, and the acceleration negative 0.4, no, negative 4, not 0.4, excuse me, negative 4 meters per second squared. And the question in part C said determine the velocity and acceleration when it moved halfway. And it's a perspective thing again. If you took it halfway from the other end, those values could be both positive. What really matters is the magnitude. Whether we're coming from the right or from the left, from stretched to compressed, halfway we'd be at a magnitude of 0.35 meters per second for velocity and a magnitude of 4 meters per second squared for acceleration. So I'm not real concerned about the signs on those, but just that you get the idea of those. All right, and finally, finishing off part D, it says find the total energy, potential energy, and kinetic energy at this position. That would be the 0.01 position. So I know this is a little small here. Let's see if I can make it bigger. Okay, at this position, remember in our energy formula, the total energy is the total at any given moment of potential kinetic, but it also tells us those totals equal 1/2 k times the amplitude squared. Since we have those values, we could easily find it that way. So we plug in the k, we plug in the amplitude released from, and we would get the total mechanical energy as 0.04 joules. And then we could do kind of each part separately. Potential energy of a spring is 1/2 kx squared. So at this position of the 0.01, which is being asked, we would have a potential of 0.01 joules when we run those numbers through that simple formula. And for kinetic energy, just simply 1/2 mv squared, we'll have to go back and use the V we found at that 0.01 position back in part C, plug it in there and get 0.03 joules. And although not asked, we should see the connection. Remember, what we found to begin with was the total energy at any given moment, 0.04. Well, that any given moment in this case is the position x equals 0.01. So if we add at that position 0.01 to 0.03, it's not a coincidence that total's 0.04. That's the point, as long as there's no friction or no significant resistances. I hope this explanation helps us, and we'll be going on to example 13.5 in the next video.